Hello everyone, so we will discuss to you the assay of volatile oils, and we are the group C. So what is volatile oils? Volatile oils, also known as ethereal oils or essential oils, in some cases as essences. Volatile oils are generally complex products composed of mixtures of compounds of widely variant chemical characteristics. The most important chemical components of official volatile oils: hydrocarbons, occasionally of the acyclic series such as heptane and myserine, but more often of the isocyclic series. Example: pinene, limonene, bornylene, fechine, dipentene, sylvestrine, and philandrine. Alcohols, present in both in the free state and in combination with acids as esters. The most generally found in official volatile oils are linalool, geraniol, citronellol, terpineol, borneol, menthol, and xanthol. Aldehydes such as benzaldehyde, cinnamic aldehyde, salicylaldehyde, citral, and citronellal. Ketones, the most important being camphor, carvone, phenone, tujone, and menthone. Phenols such as anethol, eugenol, carvacrol, safrole, chavicol, and thymol. Acids, it is sometimes present in the free state in small quantities, those occurring most commonly being acetic, propionic, butyric, valeric, benzoic, cinnamic, hydrocyanic acids, more often occurring in combination with the alcohols mentioned under 2 as esters. Example: linallyl acetate, bornyl acetate, and methyl acetate. Sulfur compounds such as allyl isothiocyanate or mustard oil. So what is the analysis for volatile oils? The analysis of volatile oils for the purposes of determining their purity and value is based on the measurement of certain physical characteristics, on the quantitative estimation of certain components such as alcohols, phenols, esters, and aldehydes, and on the qualitative test for the various substances commonly employed as adulterants. And lastly, methods of general applications of volatile oils. The purity and quality of volatile oils may be judged to some extent by their appearance, odor, color, and etc. Determination of the specific gravity, rotatory power, refractive index, solidifying point, solubility, and behavior on distillation is of much greater importance.
The specific gravity of a volatile oil may be determined with the Westphal balance or a pycnometer, the latter being the official method and the more accurate of the two. Ang Westphal balance is used to measure the buoyancy. Yung buoyancy is the ability or tendency to float sa water or sa air or sa other some fluid, and expressed as the ratio of the weight of the volume of oil to that of an equal volume of pure water when both are determined at 25 degrees Celsius. Ang specific gravities of official volatile oils vary approximately between 0.84 and 1.2. Oils which lighter than water are orange, caraway, coriander, lemon, turpentine, and rosemary oils, enriched to hydrocarbon, alcohol, esters, and ketones. So, oils with the specific gravities that approach or exceed 1.0, example is anise, cinnamon, clove, and sassafras oils, usually contains chiefly aldehydes, phenols, phenolic derivatives, and certain esters. The specific gravity of any volatile oil is not absolutely constant, since gas is influenced by such factors as the maturity of the plant from which the oil is obtained and the age of that oil, as well by the methods of preparation and purification. The rotatory power. The rotatory power of a volatile oil is generally measured with the Laurent half shadow polarimeter. Ito yung accurate measurement ng optical activity by helping you determine yung exact position of the equal brightness ng two halves. Hindi mo accurately ma-judge yung position ng maximum brightness without using half shade plate, kasi with it can lead the accurate measurement measurement ng optical activity by helping you determine the exact position of the equal brightness of the two halves using ng sodium light and tube of 10 cm long. But for highly colored oils, tube 5 or even 2.5 cm long may be used. Observation of optical activity of official oils should be at 25 degrees Celsius. Ang slight deviations from this temperature do not greatly affect the rotatory power of a volatile oil, except in the cases of lemon oil and orange oil. The rotatory power of some volatile oils varies within relatively wide limits. This determination should never be omitted in their examination. However, since it's frequently kasi serves as a valuable means of detecting adulteration with inactive substances such as alcohol or with substances of rotatory power different from that of the oil being examined. Examine lemon oil plus 57 to plus 65.6 degrees Celsius adulterated with turpentine oil is about plus 25 to negative 40 degrees Celsius. Next is refractive index. The refractive index of a volatile oil is most commonly determined by means an Abbe refractometer. This is a device that used for optical rules para ma-determine yung refractive index. The measurement of the active indices of official volatile oils is required to be performed at 20 degrees Celsius, except sa case ng rose oil which is measured at 30 degrees Celsius. The index of refraction does not vary greatly with different official volatile oils, the values being between about 1.46 and 1.61 at 20 degrees Celsius. In some cases, however, this determination may serve in the detection of extraneous matter. Next is congealing temperature or point. The congealing temperature or point of a volatile oil is determined by the method described under congealing temperature in the USP. Most essential oils solidify only at low temperatures. Consequently, in the practice, this determination is carried out with only a few oils, such as anise oils, eucalyptus oils, and fennel oil, which contain large amount of the readily crystallizable constituent anethol and eucalyptol. The higher the congealing temperature of these oils, the more they are valued. An abnormally low congealing temperature of unessential oils indicates the partial removal of the characteristic constituents for which the oil is valued or the addition of extraneous matter such as alcohol.
Distillation range or limits. The distillation range of a volatile oil is determined by the general method described under boiling and distilling ranges in the USP. Volatile oils are composed of mixtures of hydrocarbons, alcohols, esters, and etc. Boiled between certain limits of temperature are frequently separated widely. Consequently, the official standards usually designate the temperature or range of temperature at which a definite percentage of the oil distills. So dito, kakailanganin natin ng nararapat na temperature at yung definite percentage of the volatile oil na pareho silang i-distill para makuha yung desired na outcome. So for example, not less than 10% of pine needle oil should distill below 165 degrees Celsius. Fractional distillation. Fractional distillation is resorted to occasionally when determining purity of volatile oils. It serves either to separate the various components of volatile oils or to detect adulteration. Thus, alcohol and petroleum ether, both of which boil below 100 degrees Celsius, may be separated and identified in this way. The addition of turpentine oil and other adulterants may be detected by collecting various fractions of the oil and determining the rotatory power and refractive index of each fraction. For example, is orange oil and lemon oil. So to make it simple, the process of fractional distillation is a technique used to isolate or purify various components present in essential oils. Fractional distillation separates the volatile oil in different fractions or portions at various boiling points. The essential oil is evaporated in the fractioning column and its vapors are allowed to condense at different temperatures. Solubility of an volatile oil. These are generally soluble in organic solvents such as absolute alcohol ether, chloroform, benzene, carbon disulfide, and etc. They dissolve more or less readily in dilute alcohol according to the nature of their components. Oils that are containing a large percentage of oxygenated substances often produce turbid solutions with petroleum ether or carbon disulfide because of the separation of water, small quantities of which are dissolved in such oils. Practically, all the volatile oils exhibit almost constant solubility in 90, 80, or 70% alcohol. The solubility of a volatile oil in dilute alcohol frequently gives valuable data relative to its purity. Since the commonly used adulterants, turpentine oil, petroleum oils, and fatty oils are but slightly soluble in 80 or 70% alcohol. A number of volatile oils are evaluated on the basis of their ester content. The esters found are mostly the acetates of alcohols of the formula eucalyptol, for example, menthol or citronellol, or L-menthol, for example, is xanthalol. When these esters are refluxed with alcoholic potassium hydroxide, they are saponified and yield the free alcohol and the potassium salt corresponding to the acid component of the ester. The number of milligrams of potassium hydroxide required to saponify 1 gram of the oil represents the ester value or ester number of the oil. The ester value for any given oil may be subject to considerable variation, but the minimum requirements set by the official standards must be complied with when the oil is represented as a product conforming to USP or NF standards. Determination of the total esters when taken in conjunction with the official test for purity serves to detect adulteration and to establish the quality of oils valued for the ester content. Ester values of oils that contain appreciable amounts of aldehyde or phenols cannot be estimated accurately by saponification with an alkali, since variable amounts of the latter are consumed by reaction with the aldehyde and phenols or their decomposition products.
Exercise 14.1. To prepare 0.5 normal alcoholic potassium hydroxide. Materials required includes 2.5 grams of lead acetate, 1,500 ml of alcohol, and 40 grams of potassium hydroxide. So here's the procedure. Dissolve 2.5 grams of lead acetate in 5 ml of water. Add the solution to 1,000 ml of alcohol contained in a glass stoppered bottle and mix thoroughly. Dissolve 5 grams of potassium hydroxide in 25 ml of warm alcohol, cool the solution, and add it slowly without stirring to the alcohol solution of lead acetate. After 1 hour, shake the mixture vigorously. Allow it to stand overnight, decant the clear liquid, and recover the alcohol by distillation. The potassium hydroxide converts any acids present into non-volatile salts and causes the polymerization of aldehydes. The lead acetate is decomposed by the potassium hydroxide with the formation of lead oxide and potassium acetate. The lead forms insoluble and non-volatile compounds with any sulfur compounds present. The lead oxide carries down the polymerized aldehydes when it is precipitated, so it is easy to decant the clear supernatant liquid. So next, under procedure, dissolve about 35 grams of potassium hydroxide in 20 ml of water and add sufficient aldehyde-free alcohol to make 1,000 ml. Allow the solution to stand in a tightly stoppered bottle for 24 hours. Then quickly decant the clear supernatant liquid into a bottle provided with a well-fitting stopper and standardized as follows. Traces of aldehydes remaining in the alcoholic potassium hydroxide solution are polymerized and settle out when the mixture is allowed to stand. The rubber stopper used should be washed with a small quantity of the alkaline alcoholic solution before it is inserted in the mouth of the bottle to dissolve sulfur and any other material that might affect the concentration of the solution. The third procedure is measure accurately from a burette about 25 ml of 0.5 normal hydrochloric acid, dilute with 50 ml of water, add 2 drops of phenolphthalein TS, and titrate with the alcoholic potassium hydroxide solution until a permanent pale pink color is produced. Calculate the normality. So, take note also that the prepared solution should be preserved in tightly stoppered bottles to prevent changes in the concentration of alkali through absorption of carbon dioxide. Well-fitting stoppers may be used. It should also be protected from light to prevent the development of reddish compounds which interfere with correct determination of the endpoint during titration. The solution should be standardized as a blank determination whenever it is used, and it should always be measured at the same temperature at which it was standardized, since alcohol has a high coefficient of expansion. So here's the table 14.1, the official volatile oils assayed for their ester content. So under USP, we have the methyl salicylate, peppermint oil. Under national formulary, we have lavender oil and pine needle oil. We may now move on to exercise 14.2, assay of peppermint oil for total esters. The materials required includes 10 ml of peppermint oil, 25 ml of 0.5 normal alcoholic potassium hydroxide, and about 25 ml of 0.5 normal hydrochloric acid. Here's the procedure. First, place about 10 grams of peppermint oil accurately weighed in a 250 ml Erlenmeyer flask. Add 10 ml of neutralized alcohol and 2 drops of phenolphthalein TS, then add dropwise 0.1 normal sodium hydroxide until a faint pink color appears. Add 25 ml of 0.5 normal alcoholic potassium hydroxide, connect the flask to a reflux condenser, and heat on a boiling water bath for 1 hour. Instead of weighing the oil directly in a previously tiered Erlenmeyer flask, it may be weighed by difference using a 1 ounce dropper bottle from which to transfer the sample instead of a weighing bottle. The esters of peppermint oil, which consist chiefly of methyl acetate, are saponified by the alkali when the mixture is refluxed, forming free menthol and potassium acetate. Alcoholic potassium hydroxide is used because the oil is soluble in strong alcoholic solution. Second procedure, allow the mixture to cool. Add 20 ml of water and 3 drops of phenolphthalein TS and titrate the excess alkali with 0.5 normal hydrochloric acid. Perform a blank determination with the same quantities of the same reagents and in the same manner, disregarding the 0.1 normal sodium hydroxide. Each milliliter of 0.5 normal alcoholic potassium hydroxide consumed in the saponification is equivalent to 99.15 mg of total esters calculated as methyl acetate. The blank determination should be carried out at the same time the sample is being run, using the same volumes of reagent solutions in similar flask and reflux times and under the same conditions, except that the sample must be omitted. The purpose of the blank is to eliminate as far as possible errors from every source, such as those which would be introduced by the absorption of carbon dioxide by the alkali or by the alkalinity of the glass. The calculation for the determination of percent methyl acetate is illustrated as follows. Here's the example. Calculate the percent methyl acetate if a 9.120 grams sample of peppermint oil reflux with 25 ml of about 0.5 normal alcoholic potassium hydroxide required 21.52 ml of 0.4900 normal hydrochloric acid for the residual titration. The blank was run using the same volume of 0.5 normal alcoholic potassium hydroxide and required 26 ml of 0.4900 normal hydrochloric acid to bring about the endpoint. Here is the solution. First, determine the number of milliequivalents of potassium hydroxide required to saponify the esters in the sample. First, multiply 26 ml to 0.4900 and we have come up with their product as 12.740 milliequivalents hydrochloric acid, also potassium hydroxide. Multiply also 21.52 ml to 0.4900 and their product is 10.545 milliequivalents of hydrochloric acid, also potassium hydroxide. The next one is subtract 12.740 to 10.545 milliequivalents and the answer is 2.195 milliequivalents of potassium hydroxide. The number of milliequivalents of potassium hydroxide required to saponify the total esters calculated as methyl acetate. Second step is multiply 2.195 milliequivalents of potassium hydroxide so consumed by 0.19831, the weight in grams of 1 milliequivalents of methyl acetate. Observe that in the balanced chemical reaction, 1 mole of potassium hydroxide saponifies 1 mole of methyl acetate, and the number of milliequivalents of potassium hydroxide consumed represents the number of milliequivalents of methyl acetate present in the sample. So, multiply 2.195 milliequivalents to 0.19831 grams per milliequivalents and the answer is 0.4353 grams methyl acetate. The third step, divide the weight of methyl acetate by the weight of the sample and multiply by 100 in order to obtain the percentage of total esters. So 0.4353 grams methyl acetate times 100 divided by 9.120 grams, the answer is 4.77%. Next step is combining all mathematical operations from step 1, 2, and 3 and factoring. So, from here, same lang din naman sila ng nakuha ng percentage dun sa step 1, 2, and 3 natin. So, nasa sa inyo na if kung ano ang pipiliin yung formula if the long method or the shorter one. But then, we also have an alternative solution. First, determine the number of milliliters of exactly 0.5 normal alcoholic potassium hydroxide consumed by the sample. Under blank titration, multiply 26 ml to 0.4900 and then divide to 0.5000. The answer is 25.48 ml hydrochloric, also potassium hydroxide. Under residual titration, multiply 21.52 ml to 0.4900 and then divide to 0.5000. The answer is 21.09 ml hydrochloric acid, also potassium hydroxide. And then yung nakuha nyo under blank titration and residual titration, subtract them. And then we have come up with an answer of 4.39 ml. The milliliters of exactly 0.5 normal potassium hydroxide consumed in the saponification reaction. Next step is multiply 4.39 ml by 0.09915, the number of grams of methyl acetate equivalent to 1 ml of 0.5 normal alcoholic potassium hydroxide consumed. 4.39 times 0.09915 grams is equal to 0.4353 grams methyl acetate. And then the next step is continue as in step 3 of the previous calculation. So, gagawin nyo lang din kung ano yung ginawa sa step 3, which is divide the weight of methyl acetate by the weight of the sample and multiply by 100 in order to obtain the percentage of total esters. So, we have come up with an answer of 4.77%. So, siguro nagtataka kayo saan nakuha yung 0.09915 grams. So, balikan nyo lang yung table 14.1, makikita nyo dun kung saan nakuha.
So, for the assay of peppermint oil for total menthol, which is used for the determination of the menthol in the oil of peppermint. So, the materials required are 10 ml of peppermint oil, 10 ml of acetic anhydride, 1 gram of anhydrous sodium acetate, 11 grams of sodium carbonate, 3 grams of anhydrous sodium sulfate, 50 ml of 0.5N alcoholic potassium hydroxide, 50 ml of 0.5N hydrochloric acid, and an acetylization flask of about 100 ml capacity with an air condenser about 100 cm long. So the procedure: first, place 10 ml of peppermint oil in an acetylization flask of 100 ml capacity and add 10 ml of acetic anhydride and 1 gram of anhydrous sodium acetate. Then, boil the mixture gently for exactly 1 hour. Cool. Then, transfer the mixture to a small separator for rinsing the acetylization flask with 3 successive 5 ml portions of warm water and add the rinsing to the separator. So, yung acetylization flask ay dapat supported ng asbestos board habang pinapainit para ma-prevent yung decomposition ng oil. So, yung acetic anhydride ay magre-react sa menthol, kaya magfo-form ng methyl acetate and acetic acid. The acetylization is promoted by the anhydrous sodium acetate. When the liquids have completely separated, reject the water layer and wash the remaining oil with successive portions of sodium carbonate TS diluted with an equal volume of the water until the last washing is alkaline to 2 drops of phenolphthalein TS. Dry the resulting oil with anhydrous sodium sulfate and filter. Then transfer 5 ml of the dry acetylized oil to a tiered 100 ml Erlenmeyer flask. Note its exact weight. Add 50 ml of 0.5N alcoholic potassium hydroxide. Connect the flask with a reflux condenser and boil the mixture on a water bath for exactly 1 hour. Then, allow the mixture to cool, then 10 drops of phenolphthalein TS, then titrate the excess alkali with 0.5 and sulfuric acid. Tapos, perform a blank determination with the same quantities of the same reagents. And in the same manner, calculate the percentage of total menthol in the oil tested by the formula. So, ayan yung formula, yung AX 7.813 over B minus AX 0.021 times 1 minus E times 0.0021. So, para mas ma-i-explain ng maigi yung formula na yung AX ay A times 7.813 over B minus A times 0.02 times 1 minus E times 0.0021. Ayan, alamin natin. So, yung A, yan lang yung sagot na nakuha natin sa pag-subtract ng nakuha natin nagamit natin sa titration at dun sa natira. So, isusubtract mo lang yung number of milliliters of 0.5 and hydrochloric required in the above titration from the number of milliliters of 0.5 and hydrochloric required in the residual titration blank. So, ayun. So, number of ml or milliliters of 0.5 and hydrochloric then isubtract mo lang siya sa subtract yan, isubtract mo lang siya sa number asan na yun? Number of milliliters of 0.5 and hydrochloric of ml of HCl. Ayan, ito yung residual. So, yung ito residual. Then, ito yung nagamit sa taas. Yung titignan mo dun sa biret. Tapos, at yan yung A. Yan yung paano mo makuha yung A. Ayan. Ito namang B. Yung B yan yung weight of acetylated oil taken. And itong E, ito naman yung percentage of esters calculated as methyl acetate. So, ito namang 7.813 ay nakuha sa molecular weight of menthol. Which is 156.27. 1 milliliter of 0.5 and potassium hydroxide is equivalent to 156.27 over 2 times 1,000. So, equals 0.07813 ang magiging sagot niya. 0.07813 grams of menthol. Tapos, i-times mo sa 100 para maging percent siya. So, yung sa 0.021 yan. Mali. So, basta 0.021 dapat yan, which is corrects for the weight of acetyl radical in the sample of acetylized oil. The factor 0.021 being the amount of acetyl radical equivalent to 1 ml of 0.5 and potassium hydroxide. The latter is obtained from 193.31, which is yung molecular weight of methyl acetate. I-minus mo sa 156.27, which is the molecular weight of menthol. So, ang magiging sagot niyan is equals to 42.04, which is yun yung molecular weight of the acetyl radical. So, yung 0.0021 naman ay nakuha sa ratio of weight of acetyl radical to that of methyl acetate. 42.04 over 198.31 is equals to 0.21. So, dun nakuha. Tapos, yung if E, the percent of total esters determined by the preceding assay, is found to be 5, then the formula will be 1 minus 0.05 times 0.21 or 1 minus 5 times 0.0021. So, applying this correction, the formula becomes yung A times 7.813 over B minus A times 0.021 times 1 minus 5x ay times 0.0021 equals yung percent total menthol. The importance of the correction 1 minus 0.05 times 0.21 may be seen in the following example. A sample of peppermint oil found to contain 5% total esters calculated as methyl acetate and 50% total menthol as calculated from the formula. Yung percent is equals to percent of total menthol is equals to A times 7.813 over B minus A times 0.021. This gave the following percentage of total menthol when the correction was applied. 50 times 1 minus 5 times 0.0021 is equals to 50 times 1 minus 0.0105 is equals to 50 times 0.9895 is equals to 49.475% menthol-free and as esters. The correction involves about 1/2 of 1% menthol or 50 minus 49.475 is equals to 4.525%. 0.525%. So, peppermint oil is official in the USP and must contain not less than 50% total menthol in order to meet official requirements. So, sa exercise 14.3, assay for aldehyde content naman, aldehydes like ketones form addition products with certain reagents, and this property is utilized in their assay. When no other constituents are present which react with the reagent, the assay for aldehydes may be performed by the bisulfite method described later in this chapter under the assay for ketones. Thus, the cinnamic aldehyde content of the official cinnamon oil is determined by this method, the basic reaction. So, the bisulfite addition product dissolved in water, leaving the non-aldehyde constituent as a water-insoluble layer. The volume of this water-insoluble layer is then measured in Kasha flask. The Kasha flask is a glass flask of about 100 ml capacity with a long narrow neck, graduated to 10 ml in 0.1 ml divisions. In the assay of aldehydes and ketones by the bisulfite method, the portion of the oil that does not react to form a water-insoluble addition product rises to the surface, and when the flask is filled, this oil layer rises into the graduated neck of the Kasha flask, where its volume can be measured. The volume of residual oily layer subtracted from the volume of the sample oil used represents the volume of the aldehyde constituents that formed a water-soluble addition product with the bisulfite. So, sa exercise 14.4, assay of benzaldehyde, so, the materials required are 1 ml of benzaldehyde, 100 ml of hydroxylamine hydrochloride solution, bromophenol blue TS, and 1N sodium hydroxide. So, the procedure is transfer about 1 ml of benzaldehyde to tiered glass stoppered weighing bottle and weigh accurately. Then transfer from weighing bottle and content to a 250 ml Erlenmeyer flask containing 25 ml of reagent. Rinse down the sides of the flask with an additional 50 ml of the reagent. Then allow to stand for 10 minutes. Add 1 ml of bromophenol blue TS. Then titrate the liberated hydrochloric acid to a light green endpoint with 1N sodium hydroxide. Since benzaldehyde reacts mole for mole with hydroxylamine each milliliter of 1N sodium hydroxide used by the sample but not by the blank. In example, the difference is equivalent to 0.001 mole of benzaldehyde or to 106.1 milligrams. So, only 2 of the official volatile oils are assayed for their ketone content. The determination is made by the bisulfite addition reaction or by the hydroxylamine method. And that's it for my report. Thank you for listening.
Good morning, everyone. My name is Cassidy Magbanma, and for my assigned topic, it's exercise 14.5. Its object is the assay of caraway oil. Little background for this topic. Caraway oil is used for digestive problems including heartburn, bloating, gas, loss of appetite, and mild spasms of the stomach and intestines. Also, it is used for cough, improve control of urination, to kill bacteria in the body, and relieve constipation. This essential oil is extracted from the seeds of caraway plant. Caraway is possible safe when used as medicine in short term. It is usually tolerated. So for this assay, we have the materials required like a 100 ml of Cassia flask, 10 ml of caraway oil, a 100 ml of saturated sodium sulfite solution, 40 grams in 100 ml, and a 100 ml of sodium bisulfite solution in 5%. Moving to the procedure, step 1, we weigh accurately a 10 ml of caraway oil. We put it into a Cassia flask and add 50 ml of saturated solution of sodium sulfite, which has been carefully rendered neutral to 2 drops of phenolphthalein by means of a saturated sodium bisulfite solution. Then we heat the flask in a boiling water and shake it repeatedly. By the addition of few drops of saturated sodium bisulfite solution, it neutralizes the mixture from time to time. Okay. Remember this part. It's the carbon. It is the principal ketone present in the oil. It reacts with sodium bisulfite and forms a water-soluble addition product as follows, as you can see here in the structure. Continuing, if you read this part of the book, it explains that the final addition product results from the reaction of the ketone with sodium bisulfite. Even the chemical reaction is run by the sodium bisulfite. Remember that the reaction is to take place in a saturated solution of sodium sulfite. This acts to salt out from the aqueous phase those volatile oil constituents which did not react with the bisulfite. Since the volume of the water insoluble constituents is an experimentally determined volume, it is important that as little as possible it remains in the aqueous solution. The accompanied use of sodium sulfite with sodium bisulfite in this determination also provides a convenient device whereby the end of the addition reaction is readily determined with no coloration appears upon adding a few drops of phenolphthalein to the reaction mixture and heating for 15 minutes. Next. Okay, this structure explains that the sodium sulfite is hydrolyzed in part by the water with the formation of sodium hydroxide. Also, this structure explains that the presence of free alkali in the aqueous layer renders the solution basic, hence it turns pink. Upon the addition of sodium bisulfite, the above reaction proceeds left and an excess of bisulfite again renders the solution acidic. Okay, proceeding to the next step. So, after you heat it for 15 minutes and if there's no coloration appears upon adding a few drops of phenolphthalein, you cool the mixture to room temperature, and when the liquids have separated completely, take note of that, add sufficient sodium sulfite solution to raise the lower limit of the oily layer within the graduated portion of the neck of the flask. Note the volume of the residual oily liquid. This volume does not exceed 5 ml, indicating the presence in the caraway oil of not less than 50% by volume of carbone. Next. The difference between the volume of oil used as the sample and the volume of the oily layer that remains insoluble represents the carbon which dissolves in the aqueous layer. If drops of oil adhere to the walls of the flask, they may be made to rise into the neck by gently tapping and rotating it. If the residual liquid measures 4.5 ml, the percentage of carbon by volume in the oil will be 55%. So, how did we do that? By the 10 ml of caraway oil minus the residual liquid that measures 4.5 divided by 10 times 100, you can have 55%. Another official oil evaluated for its ketone content is spearmint oil. It is acid in exactly the same way as is caraway oil. It is required to contain not less than 55% by volume of carbon. For my another topic, it's exercise 14.6. Its object is the assay of clove oil. Traditionally, clove oil has been used for easing digestive upsets, relieving pain, and helping with respiratory conditions. Research has found that clove oil may have benefits for dental and topical applications, for treating infections, and even fighting cancer. So for this assay, we have the material required like a 100 ml of clove oil, a 150 ml of potassium hydroxide TS, and a Kasha flask again. For the procedure of this assay, we have a 150 ml Kasha flask, the neck of which is graduated from 0 to 6 ml at intervals of 0.01 ml. Pipette 10 ml of clove oil, then add 75 ml of potassium hydroxide TS, then shake the mixture for 5 minutes and heat it for 10 minutes in boiling water, shaking the flask at least 3 times during the heating. Remove the flask from the bath and cool to room temperature. And as you can see here in this structure, the potassium hydroxide reacts with the phenol eugenol as follows. The mixture is heated on a water bath for 10 minutes to saponify any eugenyl acetate present. Okay, for the next step, when the liquids have separated completely, add sufficient potassium hydroxide TS to raise the lower limit of the oily layer within the graduated portion of the neck. After standing for 18 hours, the volume of the oily layer does not exceed 1.5 ml, indicating the presence in the oil of not less than 85% by volume of total phenolic substances. To explain this, we have the potassium eugenolate dissolves in the water, leaving undissolved hydrocarbons, ketones, etc., which rise into the graduated neck of the flask and are measured. If stronger solutions are employed, the results obtained are too high since the strong alkali exercises some solvent action on the non-phenolic constituents, particularly on oxygenated compounds. The volume of the undissolved liquid subtracted from the volume of oil used as the sample gives the volume of eugenol that dissolved in the alkali. So, for example, we have 10 ml sample of oil yields 1.4 ml. So, then we have 10 minus 1.4 is equals to 8.6 ml of eugenol dissolved, and the percentage of eugenol in the sample is 8.6 ml divided by 10 times 100 we will have 86%. And clove oil is official in the USP. Moving on to the determination of volatile oil content of crude drugs and oleoresins, certain crude drugs and oleoresins used as medicinal or flavoring agents owe their virtues primarily to volatile oil constituents. Official assay methods for drugs and preparation of these types have been developed, and the limits for volatile oil content have been fixed in a number of instances. The methods prescribed for these determinations consist essentially of the separation of the oil from the other components of the drug or oleoresin by means of steam distillation and the accurate measurement of the volume of oil obtained. These operations are carried out in a distillation apparatus designed especially for the purpose. So, here are the volatile oil distillation apparatus. You can see here the condenser. Here we have a tube that connects for the water to enter the condenser and it will flow out eventually. Here is the asbestos covering to prevent condensation. We have here steam and oil, and the water will go here and oil will flow out here. We have a cork covered with tin foil. The materials are in a 1 liter heavy Pyrex flask. Then below of that flask is the water and bath joined in a stand. Here you can see some two apparatus. The first one is the apparatus for oils lighter than water, and the second one is for oils heavier than water. You will be familiarized with them later on as I explain their purposes. Continuing, all parts that come in contact with the material to be assayed, the volatile oil or steam, are made of glass. The condenser and receiver, as I've said earlier, are combined and are designed to minimize the loss of volatile oil through the escape of vapors and to facilitate the accurate measurement of the volume of oil in the distillate. Receivers that differ slightly from one another in design are employed, depending on whether the oil is lighter or heavier than water, as I've shown you earlier. Distillation for 4 to 8 hours is required to ensure complete isolation of the oil. The chief precaution to be observed in carrying out the determination is not to boil the contents of the flask too rapidly during distillation. Take note of that, as this causes vapors to escape around the condenser and results in a loss of volatile oil. Next. If the oil in the sample to be assayed is lighter than water, it is measured directly in the receiver, the lower part of which is shaped like a pipette and graduated in tenths of a milliliter. Let's see that. It's here, the receiver. For oils lighter than water. Next, if it's heavier than water, the oil is transferred to a graduated cylinder after distillation is complete, and the water with any remaining oil is drawn off into a small separator. The oil trap is washed with 10 ml of ether, so after all the oil is drawn, you will wash it with 10 ml of ether. The ether washings are added to the separator and the mixture is shaken and allowed to separate. The aqueous layer is drawn off and discarded. The ethereal layer is evaporated until the odor of ether is no longer perceptible. The residual oil is drained into a graduated cylinder and the volume is measured at 25 degrees Celsius. If the oil content is to be determined by weight, a small quantity of anhydrous sodium sulfate is added. The mixture is agitated gently, the clear oil is decanted, and its specific gravity is determined at 25 degrees Celsius. So that is all for my topic. Again, good morning everyone.
Exercise 14.7 to determine the volatile oil content of cinnamon. Materials required: 100 grams of cinnamon, preferably coarsely comminuted, distilled water, and volatile oil determination apparatus for oils heavier than water. Na-discuss ni Cassidy sa previous topic yung apparatus na pwede natin gamitin sa oils na heavier than water. Procedure: place 100 grams of coarsely comminuted cinnamon, accurately weighed, in the round bottom flask and fill it 1/2 with water. Add glass beads or a glass rod to the mixture to prevent bumping. Boil the contents of the flask slowly for 2 hours or until distillation is complete. So the drug should be ground to a coarse powder immediately before weighing, and the grinding should be completed as rapidly as possible to avoid excessive loss of volatile oil through evaporation. To ensure complete distillation of the oil, the contents of the flask should be boiled for at least 2 hours. Next is, after the distillation is complete, remove the separator, rotate if necessary, to cause oil droplets to settle, and read the volume to 0.1 ml. So the volume of oil represents the amount obtained from 100 grams of the drug. Now let's proceed to assay for volatile oil in spirits. The estimation of the volatile oil content of certain official spirits is based upon the separation of the volatile oil by means of an immiscible solvent and measurement of the volume of the oil as illustrated in the following exercise. Exercise 14.7 Assay of peppermint spirit. The materials required are 5 ml of peppermint spirit, Babcock bottle and centrifuge, yun yung nasa second picture sa may taas, 1 ml of kerosene, 50 ml of a saturated solution of calcium chloride, about 30 grams insufficient water to make 50 ml, acidified with hydrochloric acid, and 1 ml pipette. Procedure: first is transfer exactly 5 ml of peppermint spirit to a Babcock bottle, graduated to 8%. Add 1 ml of kerosene from a pipette calibrated to deliver that amount and mix well. Then add sufficient saturated calcium chloride solution, acidified with hydrochloric acid, almost to fill the bulb of the bottle. Rotate the bottle vigorously to ensure thorough mixing. Then add sufficient of the calcium chloride solution to bring the separated oil into the neck of the bottle. The acidified calcium chloride solution, when added to the alcoholic spirit, throws the volatile oil out of the solution, and the oil dissolves in the kerosene when the mixture is shaken. The calcium chloride serves to salt out any volatile oil from the diluted alcoholic mixture. The acid ensures the absence of alkali, which would render acids, traces of aldehydes, and water-soluble. The determination is carried out in a Babcock bottle, the neck of which is calibrated into 8 main divisions of 0.2 ml each. Next, centrifuge for 5 minutes at about 1,500 revolutions per minute, and then read the volume of oil in the stem. Subtract 5 divisions for the kerosene added, and multiply the remaining number of divisions by 4.2 to to obtain the volume of peppermint oil in 100 ml of the spirit. The oil kerosene layer, being lighter than the aqueous layer, rises into the neck of the flask when the mixture is centrifuged. The length of the oil kerosene layer supplies the information needed for the calculation of the percent of oil in the spirit. So, pag nag-centrifuge tayo, yung oil kerosene layer is iibabaw siya sa may neck ng flask since mas light siya sa aqueous layer. So for example, if 7.4 divisions represents the length of the column of oil kerosene in the graduated neck of the flask, the oil measures 7.4 minus 5.0 is equals to 2.4 divisions because each 5 divisions are equal to 1 ml, 5 times 0.2 ml, and 1 ml of kerosene was added. The 2.4 divisions, each of which represent 0.2 ml, are equal to 0.48 ml of oil. So dito sa example natin, sabihin natin yung length ng oil kerosene is 7.4. Mag-subtract tayo ng 5 divisions, which is sinabi sa procedure kanina. So 7.4 minus 5.0 is equals to 2.4 divisions. Each 5 divisions are equal to 1 ml. Kasi 5 divisions multiplied to 0.2 ml na nasa procedure din kanina. Yung 2.4 division, each represents 0.2 ml. So, 2.4 times 0.2 is equals to 0.48 ml of oil. Since a 5 ml sample is employed, 100 ml of the spirit yielded 0.48 times 20 is equals to 9.60 ml of oil. The procedure is subject to slight error, which has been experimentally determined. Consequently, the volume of oil in scale divisions is multiplied by 4.2, 20 times 0.21 ml. To correct for the error due to solubility of the oil kerosene layer in the aqueous layer and also due to contraction of volume of the immiscible solvents when mixed. Thus, in the example given, 2.4 times 4.2 is equals to 10.08 ml of oil in 100 ml of the spirit. So, peppermint spirit is official in the national formulary. That's all. Thank you for listening.